James Webb Space Telescope is identifying objects in the dark ages that, by best measurements we have, are large, fully developed galaxies.
The universe is disappearing from our reach, and the situation only gets worse. This idea is strongly supported by the surprising data obtained from James Webb. Launched on December 25, 2021, the James Webb Space Telescope has opened up a whole new perspective on parts of our solar system and universe that are leaving astronomers baffled. From planets in our solar system to merging galaxies and deep space nebulas located millions of light-years away, NASA's $10 billion time machine takes us beyond what anything else has seen. More than expected, when James Webb focused on deep space, it detected something mind-boggling. 900 trillion stars have mysteriously vanished into the void of space, and things are getting scarier by the minute. What happened? Where did stars go? How did they utterly go without a trace? Join us as we dig deeper into the shocking discovery made by James Webb, how Webb reveals details we've never seen before, and how the disappearance of that many stars might affect our planet as well as our very future. First, you should know that the way we find and confirm the presence of distant galaxies is actually very straightforward, at least astrophysically. You simply follow these steps. First, you gather light, as much as you can, from a specific region of space for as long as you can collect it. Next, you gather that light across a wide field of view in several different filters, photometrically at first, to identify ultra-distant galaxy candidates based on where the light does and doesn't appear. Then you observe the most promising ultra-distant candidates spectroscopically, where you break the light from this object into its individual wavelengths at high resolution, to determine precisely how red-shifted the light from it truly is. And finally, based on the collected data, an inferred gravitational lensing map, and the known properties of our universe, you determine the properties of this galaxy, such as its age, its brightness, its distance, and size. Although this sounds simple, the reality is that the light you can gather, both in terms of the amount of light and also in terms of the properties of that light, is fundamentally limited by the properties of your telescope or observatory. When we look at Hubble and James Webb side by side, we can immediately see three major differences. These differences are size, as in the size of the primary mirror, color, as in the color coding applied to the mirrors and optical systems that make up the observatory, and temperature, which isn't so easy to see, but is an integral part of the telescope's design and construction. For Hubble, we have a 2.4-meter diameter primary mirror, a reflective coating that appears silvery clear in color and is optimized for reflecting optical light, and the entire observatory is coated in a highly reflective coating to reflect both ultraviolet, visible light, and infrared light away from it, which arise from both the sun, which shines on it about half of the time, as well as the Earth, which radiates heat from just 500 to 600 kilometers away. However, for James Webb, we have a 6.5-meter diameter primary mirror, a reflective coating that's gold in color, which is optimized for reflecting both near-infrared and mid-infrared light, while the observatory itself is located very far, 1.5 million kilometers from Earth, and is always shielded from the sun through a novel, passive cooling technology known as a sunshade. In addition, the mid-infrared instrument aboard James Webb is outfitted with an additional custom cryocooler, which actively cools that particular instrument down to just 6 to 7 Kelvin, making it the coldest part of the telescope. These differences translate into an incredibly different set of parameters, as far as sensitivity goes, for these two observatories. According to estimates, James Webb is about 100 times more powerful than Hubble, and its infrared lens allows it to peer much further into the deep universe and the distant past. And in a stunning observation, when James Webb focused on large regions of space that appeared blank to Hubble's eyes, the telescope has detected trillions of stars disappearing without a trace. But how? Where did they go? The two leading theories about what happened are that either they're still out there, still erupting their way through their death throes, with less luminosity and perhaps obscured by dust, or they just end their existence with a whimper, not a bang, and sink into a black hole of their own making without the light and fury. To give you a feel for this idea, we must begin with a crash course on stellar evolution. Stars generate energy through nuclear fusion processes in their cores by which they turn hydrogen into helium. When stars with at least 8 times the mass of our Sun run out of that hydrogen supply, they start fusion reactions involving other elements instead, helium, carbon, oxygen, and so on, until they end up with an inert core of iron that requires more energy be put into the fusion reaction than what it can produce. At this stage, the fusion reactions cease, and the production of energy that holds the star up evaporates. Suddenly, gravity has free rein and causes the core to collapse, while the outer layers of the star rebound off the contracting core and explode outwards, sparking a supernova that, for a few weeks, can sometimes shine brighter than an entire galaxy. Meanwhile, the collapsing core forms a compact object. This object is often a spinning neutron star called a pulsar, but under certain conditions it could be a stellar mass black hole. This is the standard story of stellar timelines. However, astronomers are now beginning to come around to the idea that some stars that produce black holes may do so without a supernova explosion. Researchers have occasionally noticed occurrences of failed supernovas, stars that begin to brighten as though they are about to explode, but which then falter and die away. Elsewhere, studies of old photographic plates as part of the vanishing and appearing objects during a century of observations or Vasco project led by Beatriz Villarroel have found dozens of stars on those old plates that simply aren't seen anymore. It's like they have vanished without a trace. Could these failed supernovas and vanishing stars be evidence for stars being almost entirely pulled into the black hole they form before they get a chance to explode? Well, maybe, some scientists believe. Interestingly, though the idea is still just a theory, it now has strong supporting evidence in the form of a strange binary system studied by Vigna Gomez and his team. Designated VFTS 243, the system was discovered in 2022 and resides in the Tarantula Nebula, which is located in the Large Magellanic Cloud. It contains a 25 solar mass star and a 10 solar mass black hole that must have been produced by a massive star that reached the end of its life relatively recently, in cosmic terms. Despite the fact that VFTS 243 contains a star that has collapsed into a black hole, the traces of an explosion are nowhere to be found. For example, the orbits of the star and the black hole in VFTS 243 around their common center of mass are still nearly circular. However, supernova explosions are asymmetric, with a little more energy produced in one direction than in the other, which should give the compact object that forms a natal kick. Such a kick would accelerate the compact object, causing its orbit to widen and become more elongated. Typically, this kick is between 30 and 100 kilometers per second, yet the black hole in VFTS 243 has, at the most, been kicked by just 4 kilometers per second. The consequences of natal kicks have been observed before in pulsars, but never before in stellar mass black holes. It is very possible that this is telling us something about how stellar mass black holes are formed, and VFTS 243 is the clearest look yet at the results of this process. Natal kicks are the product of 3 things: the ejection of debris from the exploding star, a burst of neutrinos from the star's collapsing core, and gravitational waves. However, if there was no supernova, there would be no debris, leaving only the neutrinos and the gravitational waves to provide a much smaller kick, which is exactly what we see in VFTS 243. If this is correct, then it means that many of the most massive stars in the universe, which shine so very brightly, end their lives in silent darkness as they are pulled into the oblivion of a black hole. This could also be the ultimate fate of the surviving star in VFTS 243 when it reaches the end of its life. There are also wider repercussions. The fury of a supernova. A supernova explosion is an element factory. Not only are elements such as oxygen, carbon, and nitrogen in a dying star's outer layers blasted into space where they can be recycled into the next generation of stars and planets, the intense heat and energy of the supernova shockwave can result in the formation of even heavier elements in supernova debris. For instance, one of the reasons supernovas shine so bright for so long is that the radioactive decay of nickel isotopes produced in the explosion lead to the formation of cobalt and iron. However, if some massive stars are collapsing completely into black holes without supernova explosions, then they cannot contribute to the creation and recycling of elements. Cosmochemists will thus need to factor this concept, if it is indeed true, into their models of how elements are formed and spread across space. Only then can they begin to fully understand the chemical evolution of galaxies, including our own, and how quickly the necessary elements to form planets like Earth, maybe even with life of their own made from elements produced by exploding stars, can accumulate. While the idea that stars vanish into their own black holes still needs additional evidence, there is another case that we can't rule. In the worst-case scenario, the universe is just disappearing and we're powerless to stop it. It's been nearly a century since scientists first theorized that the universe is expanding and that the farther away a galaxy is from us, the faster it appears to recede. This isn't because galaxies are physically moving away from us, but rather because the universe is full of gravitationally bound objects, and the fabric of space that those objects reside in is expanding. But this picture, which held sway from the 1920s onward, has been recently revised. It's been only 20 years since we first realized that this expansion was speeding up, and that as time goes on, individual galaxies will appear to recede away from us faster and faster. In time, they'll become unreachable, even if we journey toward them at the speed of light. When you look out at a star whose light arrives after traveling toward you for 100 years, you're seeing a star that's 100 light years away due to the fact that the speed of light is finite. But when you look out at a galaxy whose light arrives after traveling toward you for a journey of 100 million years, you're not looking at a galaxy that's 100 million light years distant. Rather, you're seeing a galaxy that's significantly farther away than that. The reason for this is that on the largest scales, objects that aren't gravitationally bound together into galaxies, groups, or clusters, the universe is expanding. The longer it takes a photon to travel from a distant galaxy to your eyes, the greater the role of the universe's expansion, implying that the most distant galaxies are even farther away than the amount of time the light from them has been traveling. This shows up as a cosmic redshift. Since light is emitted with a particular energy, and hence a particular wavelength, we fully expect that it will arrive at its destination with a particular wavelength as well. If the fabric of the universe were neither expanding nor contracting, but rather were constant, that wavelength would be the same. But if the universe is expanding, the fabric of that space is stretching as shown in the video above, and hence the wavelength of that light becomes longer. The great red shifts we've observed for the most distant galaxies have absolutely verified this picture. But we can do much more than determine that the universe has expanded and continues to expand. We can use all the information we gather to conclude how the universe has expanded over its history, which in turn tells us what the universe is composed of. Once the light leaves a distant cosmic source, the expanding universe stretches the wavelength of that light. This leads to a redshift, where the more distant objects will have their light redshift for longer amounts of time, when different components of the universe were more important. by measuring sources at a whole slew of distances, discovering their redshift, and then either measuring their intrinsic versus apparent size or their intrinsic versus apparent brightness, we can reconstruct the entire expansion history of the universe. In addition, since the way the universe expands is determined by the various types of matter and energy present within it, we can learn what our universe is made out of. 68% dark energy, equivalent to a cosmological constant, 27% dark matter, 4.9% normal, protons, neutrons, and electrons, matter, 0.1% neutrinos and antineutrinos, about 0.008% photons, and absolutely nothing else, including no curvature, no cosmic strings, no domain walls, no cosmic textures, etc. Once we know the components of the universe to this degree of precision, we can simply apply this to the laws of gravity given by Einstein's general relativity and determine the future fate of our universe. What we discovered when we first applied this to the discovery of a dark energy-dominated universe was shocking. First off, it meant that all the galaxies that weren't already gravitationally bound to us would eventually disappear from view. They would speed away from us at an ever-increasing rate as the universe continued to expand and expand and expand, unchecked by gravitation or any other force. As time went on, a galaxy would get more distant, meaning that there was an increasing amount of space between that galaxy and ourselves. The galaxy appears to move away at greater and greater speeds due to the expansion of space. But this leads to an inevitable conclusion that is even more disturbing. It means that, at a particular key distance from us, due to the expansion of the fabric of space itself, a photon either leaving our galaxy toward a distant one or approaching ours from a distant galaxy will never reach us. The expansion rate of the universe is so great that distant galaxies become unreachable to our own, even if we were to move at the speed of light. At present, that distance is only about 18 billion light-years away, as the matter and radiation density is still dropping, and so is the overall expansion rate. If you consider that our observable universe is some 46 billion light-years in radius, and that all regions of space contain the same number of galaxies as one another, it means that only about 6% of the total number of galaxies in our universe are presently reachable by us, even if we left today and traveled at the speed of light. It also means that, on average, between 20 and 60,000 stars transition every second from being reachable to being unreachable. The light they emitted a second ago will someday reach us, but the light they emit this very second never will. It's a disturbing, sobering thought, but there's also a more optimistic way to view it. This is the universe reminding us how precious every second is. It's the universe telling us that if we ever want to travel beyond our own local group, beyond the gravitationally bound set of objects made up of Andromeda, the Milky Way, and about 60 small satellite galaxies, that every moment we delay is another opportunity being lost. Of the estimated 2 trillion galaxies in our universe today, only about 6% of them are still reachable from the point of view of the Milky Way, and that number is getting smaller all the time. This also means that 94% of the galaxies in our observable universe are already out of humanity's reach, owing to the accelerated expansion of the universe caused by dark energy. Every galaxy beyond our local group, as time goes on, is destined for that same fate. Unless we develop the capacity for intergalactic travel and head out to other galaxy groups and clusters, humanity will forever be stuck in our local group. As time goes on, our ability to send or receive signals to what lies beyond in the great cosmic ocean will fade from view. The accelerated expansion of the universe is relentless, and the gravity we have isn't strong enough to overcome it. The universe is disappearing, and there's absolutely nothing we can do about it. At that time, one of the biggest existential questions we're capable of pondering is how it will all ultimately end. By observing the universe today, determining the laws that underlie it, and watching how the objects within it all appear to recede from us, we've figured out that not only is the universe expanding, but that the expansion is accelerating. As time goes on, distant objects outside of our own local group move away from us at eternally increasing speeds, eventually leading to a cold, dead, empty universe, powered by dark energy. Most of us assume, consistent with the observations, that dark energy is a constant in space, with its energy density remaining constant everywhere we look. But if dark energy strengthens with time, that would change our fate dramatically, leading to a scenario known as the Big Rip. If we want to understand what the Big Rip is, the first thing we need to understand is the motivation for considering it, the evidence for the existence of dark energy. If you imagine the universe as it was a long time ago, back in the earliest stages of the hot Big Bang, you'd find that there were two different effects vying for domination. First, there's the initial expansion rate, which works to drive everything apart as quickly as possible. And opposing it, there's the gravitational effects of all the matter and energy in the universe, working to pull everything back together and recollapse the universe. Most of us would imagine three different possible fates, akin to the fable of Goldilocks and the Three Bears. Perhaps the expansion rate is too great for the matter and energy in the universe, where the expansion rate drops but never reaches zero, as distant objects continue to recede forever. Perhaps the expansion rate is too small, leading to the universe expanding to some maximum size, then contracting, recollapsing, and ending in a big crunch. Or perhaps the universe is just right, where the expansion rate and the gravitational effects of everything balance perfectly. One more atom and it would have recollapsed, but instead, we're just one atom away from that fate. But what we observe the universe to be doing is consistent with none of them. For the first few billion years, it appeared to be consistent with that perfectly balanced scenario. But then something strange occurred. If you had been watching any particular galaxy, you would have seen the effect of the expanding universe imprinted in that galaxy's light. From the time the light is emitted until the time the light is received, the expanding universe stretches that light's wavelength, causing it to be systematically shifted towards the red. The amount of redshift is related to the cumulative amount of expansion that has occurred and can be equated with an apparent recession velocity. Over time, if you were to measure that redshift for any object at all, you would have seen it started out very large, decreased steadily over time, appearing like it was going to asymptote to zero, and then, all of a sudden, stopped decreasing after reaching some minimum value, and began slowly but steadily increasing once again, where it continues to increase, all the way to the present day. What's remarkable is that this effect cannot occur in a universe governed by general relativity if it only contains matter, both normal and dark, and radiation. Spatial curvature can't account for it either. In order to explain this observed phenomenon, some fundamentally new form of energy is required, what we call dark energy today. Perhaps the most popular, and certainly, by many metrics, the most compelling, candidate explanation for dark energy is that it's simply a cosmological constant, a form of energy with a constant energy density everywhere that's found evenly all throughout space. If dark energy is either the cosmological constant from general relativity, the zero-point energy inherent to space from quantum field theory, or another type of field, akin to a scalar or pseudoscalar field that coupled equally to the universe at all locations and at all times, then it simply maintains a constant energy density and would cause all gravitationally unbound objects to accelerate away from one another at a constant rate, with their recession velocity increasing linearly with time. If this is an accurate description of dark energy, then the fate of our universe is known to some high level of precision. All of the structures which are currently gravitationally bound, like solar systems, galaxies, and groups chart clusters of galaxies, will remain gravitationally bound, with the largest bound structures never becoming bound to one another. Things will continue to expand, and the expansion will continue to accelerate until every transition that can possibly occur happens, and no further energy can be extracted from any physical process in the universe. But this doesn't have to be the case. Our best observations, from distant individual objects, from the large-scale structure of the universe, and from the temperature and polarization data from the cosmic microwave background, when they're all combined, teach us that dark energy is consistent with a cosmological constant to a precision of about 8%. However, it's still possible that dark energy is an evolving dynamical quantity, but simply evolves in a fashion that's below the current observational threshold for detection. If dark energy does evolve, then it's possible that it will decay away entirely, returning us to that just right Goldilocks case. It will weaken and then reverse sign, leading our universe to contract in a big crunch after all. Or perhaps most fascinatingly, it could increase in strength over time, with its energy density rising as the universe continues to age. That final possibility, where dark energy strengthens over time, is the one that leads to a big rip, where structures that would otherwise be stable in the universe reach an inevitable point where the expansion of the universe can eventually tear them all apart, each and every one. For many, many billions of years, the only difference between a universe with constant versus increasing dark energy will be in how the expansion rate changes, how severely the light from distant objects gets redshifted. With constant dark energy, the redshift increases linearly with time, whereas with increasing dark energy, the redshift increases at a greater than linear rate with time. This increase, if it occurs without any cap or limit on it, will eventually start to affect these large, bound structures in a rather unpleasant way. First, the largest, most extended galaxy clusters will start to dissociate, as the outer galaxies become unbound from the cluster as a whole, hurled off into intergalactic space. Next, the closer, more compact portions of clusters and eventually galaxy groups get ripped apart as well, until all we have left are individual galaxies. Afterwards, the individual galaxies will have their dark matter, gas, and eventually stars ripped out of them, from the outside in. The outskirts of the galaxies are stripped away first, but eventually even the cores of galaxies are stripped down to their individual star systems. Then, close to the end, individual solar systems are torn apart. The icy bodies of the Oort cloud are stripped away, followed by the Kuiper belt objects, then the outer planets, the asteroid belts, and even the inner planets. Finally, the individual structure like planets and moons are ripped apart into their constituent components. In the penultimate instance of the universe, molecules are torn apart into their individual atoms, electrons are stripped off of their nuclei, and atomic nuclei are ripped apart into protons and neutrons, which are then ripped apart into quarks and gluons, just moments before the fabric of space and time itself is demolished by dark energy. Although this might sound like a far-fetched scenario, you must remember that if dark energy strengthens over time and you have no restriction on the amount of time that can pass, then all of these occurrences are simply inevitable. The only question is when. Fortunately, dependent on the nature of dark energy and how its strength changes over time, we can calculate how long it will be before each step occurs. When it was originally proposed, that first step could have occurred as soon as 22 billion years from now, but that's been pushed out to some 60-80 billion years from now, at minimum. However, once that first step occurs, tearing apart structures on scales of about 20 million light-years, everything else proceeds rather quickly. Dark energy needs to strengthen tremendously to start overcoming the immense force of gravity. And once it can do so for the most loosely bound structures, we're talking only hundreds of millions of years before all of the galaxies are torn out of their home groups and clusters. Then, it's only tens of millions of years until stars are ripped out of their individual galaxies. Next, it's only a few months until the outer planets are ripped away from their parent stars, and weeks before the inner planets suffer the same fate. It's only in those final few minutes that our planet itself will be torn apart, and fractions of a second for molecules, atoms, and more to be ripped apart. The greater the amount of force and energy is required to tear something apart, the less time there is remaining until the universe itself comes to an end. It sounds scary and almost impossible to imagine, but the truly horrifying part is that some evidence seems to be pointing directly toward that fate. Fortunately, even if we do have a phantom energy scenario, it's not like the universe is going to tear itself apart anytime soon. With the known measurement constraints, the Big Rip wouldn't play out for hundreds of billions of years. Otherwise, while the Big Rip is just one possibility for how the universe could end, if dark energy increases with time, we have to face the facts. At some point, we're going to have to deal with energies and temperatures that are high enough that we've never explored them. In those regimes, anything that's not ruled out remains possible. The truth of the matter is that we know so little about the nature of dark energy that all we have to go off of is what observations tell us must be, and correspondingly, what cannot be, true. There really must be some new form of energy in the universe present, and it cannot be some form of matter, radiation, or spatial curvature. It must be distributed evenly throughout space and cannot be tied to matter. And it must be, within the limits of our present observations, consistent with a cosmological constant or a form of energy inherent to the fabric of space itself. But beyond that, we don't really have good constraints. Dark energy could have been present or absent during the first 150% of the universe's history after the Big Bang. Dark energy could be a leftover relic from the early days of inflation. Dark energy could be an emergent phenomenon that only became important recently. And dark energy could be constant and unchanging, or it could be slowly strengthening, weakening, or setting itself up for a transition far in the future from now. Whenever we find ourselves in a situation like this, scientifically, the only responsible option is to go out and gather more, superior data to help guide us in our quest to understand what's going on. If dark energy changes over time, it's measurements, not any theoretical gymnastics, that's going to guide our way. Until we know something more than we do today, all we can do is remain open to the possibilities, while simultaneously taking the simplest explanation as the most likely. However, all of that could change in very short order. When it comes to unjustified assumptions, we must always exercise caution, as the universe has surprised us before, and most likely will do so again. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.